Hello again, Dr. P here, and in this lecture we'll take a look at aromatic, non-aromatic, and anti-aromatic compounds. I'll introduce the concept of Huckel's rule and how that applies to identifying aromatic, non-aromatic, and anti-aromatic compounds. My alternate title for this lecture, for those of you who are Monty Python fans, my alternate title is How to Recognize Aromatic Compounds from Quite a Long Way Away. All right, I will now cease the British accent and let's start by talking about the problem with the resonance picture. Okay, so that's a bit of an elephant in the room, and I haven't really talked about said elephant yet, but let's look at cyclobutadiene. So we have alternating single and double bonds. So according to the resonance picture, we should get this. Now this is an exaggeration, but in actuality, our cyclobutadiene, where the resonance picture says, oh yeah, we can draw, and I forgot to put in my resonance arrows here, or my electron arrows here. Yeah, we could delocalize the electron density. Should be nice and stable. In actuality, we get something that's a little more rectangular, with truly alternating single and double bonds. Remember, with benzene, our bond lengths are all the same. I didn't mention that last time, but usually I mention early on in 12A, I'm talking about pi systems. Cyclobutadiene is also very unstable. Actually, it's this, and very unstable. That is, it's really, really tough to make. You have to use very low temperatures and an argon atmosphere and irradiate precursor molecules with UV light, and then you end up with individual molecules of cyclobutadiene stuck in a frozen argon matrix, and it's kind of crazy stuff. But anyway, so let's look at the MO picture instead. Now, we have 4 pi electrons, so we should have 4 pi 2, pi 3, 4 molecular orbitals. Okay, and so just like last time, I'll color these in so we can have all red here. That's pi 1. And then pi 2, we've got 2 different possible nodes. And then in pi 3, or sorry, pi 4, that's really pi 4 star. Sorry, I keep switching pens here. We've got 2 nodes and alternating single and double Sorry, alternating phases. Sorry about that. Hold on, I need more coffee. All right, and now we can fill in these these orbitals here. So 1, 2, 3, 4. Okay, this is our 0 of energy here. So here we have a bonding orbital. Up here we have an anti-bonding orbital. And in the middle we've got, let's see, non-bonding orbitals. And the issue that we have here is that we have electron density in the non-bonding orbitals. And there isn't a picture of this in the in the text, but so this will have to suffice. And it's the presence of these electrons in these unpaired electrons in the non-bonding orbitals that make cyclobutadiene so unstable. So I'm going to just write that here. Presence of unpaired, again they're unpaired because remember they spread out before they pair up, in non-bonding orbitals. Makes cyclobutadiene very unstable. And we call that anti-aromatic. All right. Now, what about some other molecules? Okay, so this doesn't work for cyclobutadiene with 4 pi electrons. The resonance picture doesn't work. And the molecular orbital picture tells us that it's not as stable. What about cyclooctatetraene? So that's going to be a stop sign like. And we could draw molecular orbitals for this. I'm not going to, but it would have non-bonding, let me rephrase that, would have electrons in non-bonding orbitals, but actually it actually looks like this. It's not planar. Okay, it's this bent sort of tub-like shape. And this is an example of a non-aromatic compound. It would be unstable and anti-aromatic if it was planar, but because it can adopt this other conformation, that actually means that it doesn't have the same types of molecular orbitals. And this leads us to our criteria for aromaticity. Okay, we have to have a continuous ring of overlapping p orbitals. The system must be planar. these overlapping p orbitals must contribute to stability. So let me just say, let's say orbitals contribute to stability. So if things are overlapping and it's planar and it's stable, then let me zoom in a little bit here just so I can see this a little bit better there. If these above criteria are met, then if we have 4n plus 2 pi electrons, that's going to be aromatic. If we have 4n pi electrons, that will be anti-aromatic. And that's Huckel's rule. Now the text doesn't really talk about anti-aromatic compounds, so I thought this was an important thing to talk about. We'll look at some examples in just a minute, but let me go over these criteria one more time. So we need to have a continuous ring of overlapping p orbitals. Yes, we have it here. Continuous ring, overlapping p orbitals. It's planar, yes. Orbitals contribute to the stability. Well, cyclobutadiene is unstable, but that's because we get our anti-aromatic, our 4n pi electrons. So n is an integer. So benzene has 6 pi electrons, which is 4n plus 2 when n is 1. Cyclooctatetraene has 8 pi electrons, so it should be anti-aromatic, but only if it's planar. So if something is not planar, or if we somehow break our overlapping p orbital, our continuous ring of overlapping p orbitals, then that will make things non-aromatic. So let's see, if one of these not met, compound is non-aromatic. All right, and let's see, I wanted to check just one more thing. You know what, I'm going to remove this criteria here, because it's like so I do apologize for that. So let me just draw some arrows there. There we go. Because we're not really actually contributing to the stability, or contributing to the overall energy, whether it's stable or unstable. But yeah, just different texts have things a little different. Ms. Gibson showed me this nice website where you can have some practice identifying aromatic and anti-aromatic and non-aromatic compounds. So I'll try to post a link to that on Canvas for you. So let's go ahead and apply Huckel's rule. Let's look at some examples. So we'll start off by identifying each of the following compounds as aromatic anti-aromatic or non-aromatic. So let me go ahead and draw a few things here. How did I want to do this? All right, so these are a few here. So let's take a look at these. And let me just get out a different colored pen. So, maybe a few different colored pens. All right, so we have here 2, 4, 6 pi electrons in a ring. Hey, we have pi electrons here, but guess what? They don't count. So we've got 6 pi electrons, so this is aromatic. Next one here, we've got 2, 4, 6, 8, 12 pi electrons. 6, 8, 12 pi electrons. And you might think this would be anti-aromatic. And I totally miscounted. 2, 4, 6, 8, 12. Come on, Wayne. 2, 4, 6, 8, 10 pi electrons. It's aromatic. How about this? 2, 4, 6, 8 pi electrons. Well, these ones don't count. We're just interested in the ones that are in a ring. So that's 6 pi electrons, and this is aromatic. How about this? We've got 2, 4, 6, 8 pi electrons. But we have this guy as sp3. So it's not a continuous ring. Yes, we have an sp3 carbon here, but it doesn't interrupt this continuous ring. Here, the presence of this sp3 carbon interrupts our ring of p orbitals. So this is going to be non-aromatic. All right, next one here. 2, 4, 6, 8 pi electrons. I'm counting correctly now. This would be anti-aromatic. Now, could it be non-planar? Could it bend? Well, not really, because of all the double bonds and the way we have the fused ring here. I would not expect this to bend. I would expect this to be anti-aromatic. Now, how about the next one? I've got 2, 4, 6, 8, 10, 12 pi electrons. So maybe I'll write it in red here. 12 pi electrons. So this would be anti-aromatic if planar. And the fact that we've got so many carbons here means that this could probably flex somewhat and adopt a non-aromatic conformation. So when you're applying Huckel's rule, remember, things go from high energy to low energy. So we've got energy here, and we've got increasing stability. So we'll say here more stable, less stable. So anti-aromatic is higher energy, less stable. Non-aromatic is lower in energy and a little more stable. And then aromatic is the lowest in energy and the most stable. So if you're faced with a choice between anti-aromatic and non-aromatic, then it could be, or rather it will be, non-aromatic. The only way you'll get something to be anti-aromatic is if you force it to be. If you make it so it can't be planar, if it can only be planar and it has to have the p orbitals, then it'll be anti-aromatic. But if it could twist up and not be planar, or if there's a way to interrupt that ring of p orbitals, then it'll be non-aromatic. And if you're choosing between non-aromatic and aromatic, if it can be aromatic, it will be. Okay, so you're not going to see too much stuff that is truly anti-aromatic. Most things would be non-aromatic or aromatic. And in the next lecture video, we'll look at some more examples. These are only hydrocarbons here. We'll look at compounds. We'll look at what we call heterocycles. So we'll look at compounds with heteroatoms, that is nitrogen, oxygen, sulfur. And we'll look at ions as well and look at aromatic ions. I do advise you to look at the practice problems because, well, what I'll be asking you on the quiz, I will be asking you to do this, to identify compounds as aromatic, anti-aromatic, or non-aromatic. All right. Well, thanks for tuning in. Until next time, stay safe out there. Bye now.